All right, let's go and get started. Let me start off by getting the sign-in sheet passed around. I will get the lights adjusted here in a minute. First, again, homework 6, it's due today. So if you haven't already turned it in, go ahead and get that in up here. Homework 7, I'm going to assign a homework on the analysis of and design of columns and frames. I'm going to assign it on Wednesday so that it'll be due the following Friday. You concrete folks have an exam on the following Wednesday, so that way you're not getting a homework and an exam on the same day. At least in my classes, I can't control anybody else. Sound fair? In concrete? Yes. No, remember I moved it back. I told you I moved it back. Well,
I think it was a great decision.
Well, I appreciate that. I do want to take one moment and talk about the Virginia's Conference. We did pretty good at the Virginia's Conference. We scored second in the transportation competition. We scored first in the concrete bowling. So you all did a fantastic job. We also scored fourth in the steel bridge. I'll show you something real quick. This is actually pretty nifty. One of the students who went on the competition created a time-lapse video that Marshall University retweeted. So let me. So it was actually on the page's Twitter account. But if you, speaking of, I figured I'd show everybody. So here you can see this is back in the old engineering building. They've set up the staging yard, and you can see that they're doing the construction. You can kind of see how they built it. They actually sort of built it diagonally and then just sort of lifted it across. Ultimately, what took the longest time really was the bracing more than anything. The lateral system was a little more intricate than the main body of the bridge. But in the end, we scored fourth. We had a very respectable score or overall cost. Last year, I pulled the numbers to make sure I was accurate. Last year, that overall cost would have gotten us to nationals. We had some really tight competition this year, but all in all, the students did very well. I guess my final message is that for those of you that are going to be here next year, I guess my dare for you is to do better. In other words, the bridge this year got a cost of, what was it, $26 million? So you all do better. You know what I mean? So if you're interested, now's the time to get involved. Now that you, I don't know, maybe have a little bit of experience with some of this steel stuff, bolts and welds and columns and beams and whatnot, you can help out. But the team did a great job, and I was tickled. So okay. Other than that, any questions about the schedule, about bookkeeping, what's coming on for now? Again, we don't have any more exams in here until the final, but there are going to be a number of homeworks. And the homeworks are going to come in pretty, I'll say, rapid succession, because we're going to have homework 7 and then homework 8 and homework 9. And so we've got 3 more homeworks for the semester. So everybody good? Okay. I'll try and get homework 6 graded as soon as possible. Also, I hope you all brought a straight edge, because we're going to use it today. I've been mentioning it for the past, 2 or 3 lectures. So hopefully you got one. If it comes down to it, you can use the edge of your manual or the edge of your book or something like that. Okay. With that, let's get into our discussion today of columns and frames. Now, let's see. Okay, so last time we discussed the difference between a singular column and a column that's part of a larger frame. Now, if you recall, we had braced frames and moment frames, really the 2 big lateral resisting systems to consider. The big thing is that this column, for instance, in this brace frame, is designed differently than, let's say, some of these columns that are back here. Some of those columns that are back there are just part of the gravity load resisting system of the building. So they're all sort of designed as if they're individual. In most cases, you can take K to equal 1 and just sort of go with it. But brace frames and moment frames are handled a little differently. Now, is everybody clear on the difference between what a brace frame is and what a moment frame is? Is everybody okay with that difference? Everybody good? Okay. Now, okay, and one other, I guess, main identification that I want you all to be able to identify is the difference between what a simple shear connection is and what a moment connection is. These moment connections over here on the right are going to be the ones that you'll see in moment frames. And the big difference between the two is that for a moment connection, your flanges are connected to the column as well. For a simple shear connection, you're only connecting the web. So really that connection is there just to transmit shear and not moment. So if you want an analytical analogy, you can sort of think of this as kind of a hinge roller type connection, and you can think of this as a fixed connection. The big difference is that the fixed connection will resist moment. The one on the left is not really designed to resist moment. I'm not saying it's going to act like the triangle and the circle in structural analysis and freely, like the roller, and freely displace, hundreds of inches if you put a load that way. I'm just saying it's not designed to resist moment, whereas this one is. Sound good? Okay. Now, I wanted to go back to this. I want to identify a couple of sort of analytical effective length cases and sort of relate that to how columns in frames behave. And I want to start off this analysis by looking at case A and case B. So case A is a column that is fully fixed on the top and fully fixed on the bottom. Okay? And if you do the analysis and go through and solve the differential equations that I know you all love to solve, right? Remember, what's the college student's #1 tool for solving diffie-q? Was it Wolfram Alpha, right? I know things. All right. For a fully fixed column, the theory states that your effective length factor K is 0.5. Now, if you take that top support or the bottom support, it really doesn't matter, you can do either one, but if you take one of those supports and you pin it, the column gets a little more flexible, and it buckles under a lower load. And we represent that through a larger effective length factor. In this case, it's 0.7. Everybody okay with that? Well, my question is, how does this behave? Okay. Well, this is a fixed end. Is that fixed? Is that pinned? Maybe it's somewhere in between. Okay. Everybody kind of get what I'm talking about there? So I propose that if you have a braced frame where, let's say, the support is fixed, and if I'm looking at the effective length factor for this column, it's not 0.5, it's not 0.7, it's probably somewhere in between, okay? And it's dependent upon what is the stiffness of all the elements framing into this joint, okay? Same thing if I pin the bottom, okay? Well, I've got a pinned support down here. This isn't fixed, this isn't pinned, it's somewhere in between. So it's probably somewhere between 0.7 and 0.1. Now that's for brace frames. You can conduct a similar analogy looking at moment frames, and you can say that if I have a fixed support and I have members framing in up top, that this is probably somewhere between fixed free and pin free, so it's somewhere between 1 and 2. And if you have a pin support on the bottom, it's probably somewhat bigger than 2. And analytically, I guess, theoretically, it could go all the way to infinity, although that really wouldn't happen in a practical setting. The math allows that. For a practicality standpoint, we have ways of sort of avoiding that we'll discuss here in a little bit. But everybody okay with the theory so far? What I'm really trying to get at is that for a braced frame, and what I mean by a braced frame, I mean by a frame where the side sway, the ability to move left and right, is inhibited. Like regardless of if I'm looking at, let's look at the brace frames. Regardless of if I'm looking at a fixed support brace frame or a pin support brace frame, the real analytical point to keep in mind is that the bottom end of the columns and the top end of the columns don't move. Okay? In other words, side sway is inhibited. Whereas for a moment frame, they do. Okay? Those top ends, you can see they're translating out, in this case, to the right. So, yes?
You're looking like one single frame here, like the pictures you're left with, are going to be stories above it, probably.
You're right.
So then it's not going to look like
You're exactly right. You're exactly right. And I'm going to discuss how we handle that here in a little bit. But you're exactly right. Okay? The question was, we're just looking at the first story. What about the second story? And the answer is I'm going to discuss how we handle that here in a little bit. But let me give you a short answer. would you agree that ultimately, regardless of if I'm looking at the first story or any story in the building, what that K is going to be a function of the stiffness of the elements framing into that joint. Would you agree with that? Okay, all right. So that's going to be how we ultimately handle it. The big point I want you to keep in mind also is, again, this also applies to either the first story or the 80th story or what have you. Analytically, the difference between a brace frame and a moment frame is that for brace frames, we're treating them as if side sway is either inhibited or uninhibited. So if you look on the handout that I provided you, the big alignment chart, I believe it says moment frame alignment chart, and then it says what? Side sway uninhibited? Everybody see that? Okay. All right. So far, so good? Okay. All right. Again, ultimately the deciding factor is the stiffness of the columns and girders that frame into that connection. Okay? So what I'm going to do is throw out a term called G. And G stands for what I'll call a rotational stiffness parameter. Now, if you remember from structural analysis, the term EI over L, like that tended to pop up a lot when we were talking about beams. And it's essentially a measure of how stiff an element is in relation to bending. So it's flexural stiffness or rotational stiffness. If we were talking about axial stiffness, it might be something like AE over L, you know, the area times the modulus of elasticity. If it was GJ over L, it'd be the torsional stiffness. Y'all remembering these terms? I know it's been a while, but I know that you use them. What I'm going to do is I'm going to define a rotational stiffness parameter for a given joint. So for instance, if I'm looking at this frame and I'm looking at this column, I'd have a G value for the top joint of the column and a G value for the bottom joint of the column. Now I'm going to say that G is the EI, the sum of all the stiffnesses of the columns divided by the sum of the stiffnesses of all the girders. So add up all the EI over L values for the columns and add up all the EI over L values for the girders and just divide them. Now, the nice thing about dealing with this type of math is this is steel design, so everything's made of steel. And if everything's made of steel, it has the same E value, so we could just cancel that out. So instead of dealing with EI over L, we can just deal with I over L. Everybody okay with that? Everybody good? Okay. Now, if you go through and go to grad school and get a graduate degree in structural engineering and go take a class in stability or a theory of elastic stability or something like that, you could probably learn how to derive equations to solve for your K value. And for braced frames, you get a K value or an equation something like this, and for moment frames, you get a K value something like this. Now, I'm not going to get into the derivation. The math gets pretty funky, and you have to make a lot of assumptions to get there. The point I want to make is these equations look a little nasty, don't they? Could you take this equation and solve for K? The Casio FX115 ES Plus, right? Or the HP50, right? RPN. The problem is these equations are actually pretty much impossible to solve analytically or closed form. Like taking just taking this equation and just solving for K, getting K on one side of the equation is pretty messy. Okay, in fact, I'd say it's really impossible. Really, the only way to solve for K is using a numerical approach. You know, one easy way of doing it is you could use something like GoalSeek or Solver in Excel, right? You could plug in a G value for A or GA, GB, guess a value for K, and just GoalSeek it until you got that equation to be equal to 0. There's nothing wrong with that at all. That would work just fine. Fortunately, the spec provides us a graphical technique that we can use, hence these alignment charts. So here's the way they work, okay? So you will look at either end of the column, and you will calculate a G value on one end of the column and a G value on the other end of the column. Locate those on either side. So this might be a G value on the left of about like 1.2, something like that. And on the right, well, we got about 5.9. So G value over here, G value over here, strike a line, and here's your K axis, and you can see K is about 1.6, 1.7, 1.8. So that's between 1.78, about like that. Everybody kind of see that? Now, right off the bat, I can see hands raising, and they go, well, Dr. Michelson, what if it's an exam and we have 1.77? We have 1.79. Does that mean we're going to get a 0? Yes. Well, of course. No, I'm kidding. Look, I'm fully aware that with interpolation, these values can be off by like a 1.79 or 1.78. That's no big deal. If you get a K value of 3.26, it's going to be some problems, right? Okay? So don't worry about that. Don't worry about your K value being off by 100. That's no big deal. Okay? Sound good? All right. Now, here's a couple special cases for G values. And this is where we're taking into account some of the differences between theory and what you really see in real life. Okay? So for a fixed support, if I was calculating the G value for, let's say, this joint, okay, I would take the sum of the stiffness of all the columns divided by the sum of the stiffness of all the girders. In this case, the girders would really be the let's say, the fixed support. Okay? A fixed support has infinite stiffness. Theoretically has infinite stiffness. So if I take a number and divide it by infinity, essentially what am I getting? 0, right? Now, what my point is that I'm saying that there is no such thing as infinite stiffness. I mean, we were in structural analysis. It's like my first lecture in structural analysis. I said, you know, I showed you all a picture of a three-dimensional panel truss, and I said, you know, here's this really complex structure, right? And then here's what we analyze in class, and it's a bunch of lines and dots and arrows and triangles, right? We make some assumptions going into the behavior of those lines and dots and triangles and so on and so forth. And for the most part, they do a good job in representing real-life behavior, but they are analytical models. We make those assumptions to make the analysis possible and easy to perform. But what I am saying is that there is no such thing as a support that is perfectly fixed, okay? There is going to be some rotation. Sorry, there just is, okay? So instead of using a theoretical value of 0 for a fixed support, anytime we see a fixed support on a problem, the G value for that joint is 1, okay? So we're a little bit more rotation. Now, on the flip side, if we have a pin support, same idea, you know, sum of the stiffness of all the columns divided by the sum of the stiffness of all the girders. A pin support is completely the opposite. A pin support, mathematically, it freely allows rotation. So it has 0 stiffness rotationally. So if you take a number and divide it by 0, technically our G value, I mean, we should be referencing all the way up here, infinity, right? But again, if we're talking about column rotation, I propose that there's nothing that's perfectly pinned either, okay? So for a pin support, the recommended value would be a G value of 10, okay? Everybody okay with that? Everybody good? Now, there are a number of assumptions that go into the development of these alignment charts. I know some of you are probably thinking, well, you gave us the moment frame chart, where's the brace frame chart? I'm going to get to that here in a little bit. There are a number of assumptions that go along with these alignment charts, and if you have a really, really complex building, sometimes alignment charts, they just aren't going to work. I mean, we make a number of assumptions about alignment charts, you know, that the members are prismatic, all the columns buckle simultaneously, and et cetera. And if you've got a really, really complex structure, these alignment charts probably aren't going to work. And in those cases, you're probably just going to have to break out some three-dimensional software, use some more refined methods like direct analysis or something like that. And that's where, I mean, grad school comes into play. This will get you through most basic moment frame columns. Now, one of these elements can be adjusted very easily, and that's elastic behavior. And I'd say that's a very important one. If you remember our column curve has an inelastic behavior component and an elastic behavior component, right? And the inelastic has that what? 0.658 raised to the Fy over Fe, all times Fy. Y'all remember that? Okay. Most columns that we design fall into that range, fall into the inelastic range. Well, these alignment charts are all assuming elastic behavior, so that's wrong. We can adjust that very, very easily through the use of a inelastic reduction factor. Now, I'll show you how this works. The idea is this. The idea is that we recognize that elastic buckling is pi squared E times KL over R squared. Well, for inelastic buckling, remember that the stress strain curve, it goes up, and remember how it teeters off like that a little bit before you get that full yielding? Well, in that yielding, in that inelastic range, we have that not the Young's modulus, but we have that tangent modulus sort of following along that curve. Y'all remember that? Well, if you go through and plug in instead of EI over L and EI over L, if we plug in that tangent modulus, we can come up with a sort of a reduction factor called tau that we can use to account for that inelastic behavior. It's pretty easy. It's a pretty plug-and-chug expression. Tau is a function of how much stress is on the column. So let's take a look at this. All right. So there's two equations there on the bottom. So let's look at the first line. If Pu over Fyag is less than 0.5, tau equals 1. Well, let's think about that. All right, first off, what's going on over here? If Pu over Fyag, what is Fyag? What's that? The resistance for what? What are we talking about? But I think we're getting too complicated. I mean, if I load a column with Fyag, what has it done? Yielded. There we go. That's the yield load, right? Okay. Now Pu is the load that we're actually putting on the column, right? So let's come up with some numbers. Let's make this simple. Let's say that it takes 200 kips to yield a column, okay? But I've only got 80 kips on it. So I take 80 divided by 200. That's going to be less than this, right? Make sense? But think, if it takes 200 kips to yield a column and I've only got 80 on it, I haven't come close to yielding it at all, have I? No. So in that instance, I shouldn't have any inelastic reduction at all, and tau's just 1. Sound good? If, however, I do have a substantial load, let's say it takes 200 kips to yield that column and I'm at 190, well, okay, we're probably going to have some inelastic behavior, or we're going to get close to some inelastic behavior. Remember, the curve sort of goes like that a little bit, and especially goes like that when you consider residual stresses and imperfections and all that stuff in your column. When that value gets over 0.5, tau's a pretty plug-and-chug expression. Sound good? Any questions? All right. So here's, if you want to account for inelastic behavior, calculate your G values, calculate tau, and then instead of going into this alignment chart with just G values, go in with tau times GA and tau times GB. So what will end up happening is instead of your line being like this, it ends up getting shifted down a little bit, okay? Which is definitely worth doing, because if tau is, let's follow this mathematically. If tau is less than 1, then your G values are going to get smaller, right? Make sense? If your G values get smaller, what happens to K? Does it get smaller? Yep. So if K gets smaller, what happens to KL over R? It gets smaller. Now, if your KL over R gets smaller, what happens to your capacity? It goes up, right? Because remember, KL over R is your slenderness. The lower the slenderness, the stronger the column, right? So if all it takes is to do a little bit of math to squeak out a little more capacity out of your column, do it, right? Make sense? Any questions? Okay. Now, let's look at this example real quick, okay? So we're going to compute K for columns A, B, and column B, C in the frame that you're seeing here on your screen. Now, let's digest this a little bit and let's see what's going on. Okay, so first off, is this a moment frame or is this a brace frame? Moment frame. Supports, what's going on with the supports? Fixed there, or they pin? Pin. All right, here we go. That's good. Now, let's talk about our axes. Are we looking at the strong axes of these columns or the weak axes of these columns? How about this? Okay, remember this symbol right here? Take a look at this. What's that and what's that? Those are the flanges. Remember this? Strong axis, weak axis. So what axis are we looking at for this frame? There we go. All right. Okay. Now we're getting somewhere. All right. Let's delve into that a little bit. Okay. So what I'm proposing is this: because all of these columns, we'll say they're all they're facing the same way. When we use this alignment chart to compute K, we're only going to be computing KX, right? In other words, K buckling, the columns buckling this way, right? Okay. Now, what about the columns buckling this way, okay? What I'm going to do for this problem is I'm going to have you all assume that the frame is a braced frame in this direction. So it's a moment frame this way, braced frame this way, okay? Now what I want you all to do is open up your manuals, and I want you to turn to the section of the code that had those K values in it. Uh-oh. Uh-oh. Woo. Uh-oh. Okay. Oh, okay. Now, does everybody see those K values? Now turn the page. Oh. Oh, look at that. Now, the caption, okay, so you see the two alignment charts? Okay, so I want you to look at the chart on the left, okay? Somebody read the caption. What's the caption say right here?
Alignment chart, sides way, pivoted, brace frame.
So the chart on the left is for the brace frame. The chart on the right is for the moment frame, right? Now, help me out with something. What is the range for the K values on the brace frame? 0.5 to 1. Does that make sense? Based on our discussion we had earlier about the range for K values for brace frames. And for moment frames, it's from 1 to infinity. Sound good? Okay. Now, what I'm saying is, in this direction, along the screen, it's a moment frame. We'll assume it's a braced frame this way. So would you agree that for columns buckling this way, sort of curving out like that or curving into the screen, that the K value's got to be somewhere between 0.5 and 1, right? But I didn't give you any of the members. I didn't give you, what size the beams or the brace or anything like that. So when in doubt, what would you assume? K is 1. Why would you assume K equals 1? Exactly. The highest K value is the most conservative, right? Higher K value, higher KLR, lower capacity. So for braced frames, I can already see the question, why didn't you give us a K chart for braced frames? Because it is very, very typical to just take K equals 1 for all those columns. I mean, you can squeak out a little more capacity once you've got your columns picked out if you want to go through the process of using the brace frame chart. But for design purposes, it's very common to just take K equals 1. Sound good? Wait, if you turn back, you need that chart.
You got it with you.
What? That's just a waste of whiteout, though. All right. Is everybody okay with this? Okay. So in order to determine G values, we're going to need moments of inertia. Now, when we look up moments of inertia for these beams and these columns, are we going to look up Ix or are we going to look up Iy? X, because this is the strong axis, okay? Make sense? So again, that's why I wanted to take some time and actually digest and just what the heck is going on with this slide, okay? Make sense? Everybody good? All right, now let's get to it. Okay, while we're at it, let's go to table 1-1. We're going to need some moments of inertia, and I'm going to have you all look them up for me. So some of you all look up the W14, some of you look up the W24s, because we notice we got W24s, we got W14s. Now, if you notice, everything's like a different size. I wanted you all to make sure you're comfortable with your bookkeeping. So we've got a bunch of different cross-sections to consider. All right, so we're on example 17. Okay, so we're going to need section properties. All right, so we're going to need, let's see, what do we got? The W14 by 90 and the W14 by 132. We're going to need Ix. Does it make sense that the W14 by 132 is on the first story and the W14 by 90 is on the second story? Columns on the bottom, see more load. So what are our Ix values? Let's start with the 14 by 90. 999. All right. And 1530. All right, what about the W24 by, was it 55? I didn't do you all any favors with this one because these are so close, right? 1350 and 1530. All right. Sound good? Okay. So what we're going to do for our notation is we're looking at what? Column AB and column AC. Okay? So we're going to need a G value for each joint. So I'm going to calculate a G sub A, G sub B, and a G sub C. Now let's keep in mind, okay, so we'll call this just the G values. Remember, G is just the sum of I over L for the columns divided by the sum of I over L for the girders. So let's start off with joint A. How many columns frame into joint A? How many columns are in joint A? One. There's only one column in joint A, right? Which column? Well, what shape is that? 14 by 90. So 999 inches to the fourth divided by, what's the length of that column? Just tell me what the length is off the drawing. Watch this. I'm going to leave it 12 feet. Oh. You see it. Now, how many girders frame in? 2. So tell me, let's do the one on the left. Is it a W24 by 55 or 68? So 1830 inches to the fourth divided by, how long is it? 40 feet. Plus the 1350. See. Divided by how long is that one? 32 feet. So right there you were saying, I'm going to convert it to inches, okay? It doesn't matter, right? Because you're taking inches to the fourth over feet divided by inch to the fourth over feet. It all cancel out. That's the nice thing about rotational stiffness parameters. Everything is consistent with your units.
So, how come we don't consider this in like a 3D sort of way? What if there's another girder framing in?
That's what I'm saying is that for the purposes of this problem, we're going to assume it's a braced frame. Okay?
So if it wasn't a brace frame, we have to consider it.
Exactly. We'd have to know. We'd have to know the member's framing in. I'm saying because it's a brace frame. If we knew, it'd be great. But if we don't know, it really doesn't matter. We'll just take K to be 1 because that's the worst case scenario. Does that make sense?
It'll make more sense later, I'm sure.
Okay. All right. Everybody else? Did anybody else have any other questions? All right. So what do we get for this? 0.947. You know, we'll just take it to 0.95 because you'll see what we're going to do with this in a second. Because this is visual. Well, I don't think we're going to get much more accurate than that. Now, GB. How many columns frame into GB? 2. So the one up top, what is it? Is it the 999 over 12? Plus, and then what, 1530 divided by what? How long is that column? I can't remember. And then the beam, or the girders, they're the same, right? And so what does that come out to be? $2.19. All right. Now what's GC going to be? Huh? No, I got to go through your notes. Come on now. 10. It's a pin support. All right, does that make sense? Okay. Now let's use our alignment chart. And I'm going to call these elastic K values. And we're going to say in the X direction. All right. So let's start off with column AB. So GA is 0.95 and GB is 2.19. So what you're going to do, go into your alignment chart, 0.095 or 0.95 and 2.19. Now you all have your alignment charts, right? And you all, of course, brought straight edges, right? Every one of you, right? So what is your KX? Now watch this. I'm going to say KX is about something. It's not exact. It's about. $1.45. What do you get? 1.46. 45? All right, okay, 1.45. Does everybody see that? All right. Now, then let's do BC. So GB is 2.19, and GC is what? 10. So here. And notice, it doesn't matter if you go left to right or right to left. It's the same scale on either side. So if you want to put 10 on the left or 10 on the, it doesn't matter. So you're going to have 2.19 and it's 10. Now keep in mind, these are logarithmic scales, so just do your best to try and eyeball that again. Keep in mind, when you're designing columns, we're just picking the next increment in that table 4.1. So if your design is really getting this close, you might bump it up a little bit. 2.05. See, okay, I got 2.14.
I was thinking 2.15.
Yeah, it's a 2.5 because it's like 0.2.
Keep in mind, make sure you're reading those marks right, because go between 2 and 3, how many tick marks do you have? Ooh, those aren't tenths, those are 2/10. Oh. Mistake counters back to 2 at this point. They're like, yeah, about that. All right. Does anybody have any questions? Okay. Now, those K values, we can drop them a little bit if we take into account our inelastic stiffness. Okay. Now, I'm going to show you how this this works. Okay. Does everybody have all this? Okay. So let's make an assumption. Okay. So we'll say, bless you, for the purposes of this problem, assume the following. So let's say you ran your RISA analysis or did your structural analysis, what have you, and you get that for column AB, the design load is 1050, and for column BC, your design load is 1370. So I'm just giving you some loads for the purposes of seeing what's going on with these columns. Can we do a little better on our K values? Remember, we want our K values to be as low as possible. Lower K means higher capacity. All right. Everybody good for this? Now, can I go ahead and go on to the next slide? All right. In order to do K values using inelasticity, I'm going to need areas for each of those columns. So we'll say tau values. So for the W14 by 90 and the W14 by 132, what are the areas? Okay. Sound good? Oh, it doesn't really stand for anything. In the simplest term possible, I'll say this. Tau values are empirical expressions, and they've undergone changes over different editions of the specification. So they handled that by just calling them with different subscripts. So we're on B. I'm telling you, that's really it. In the previous manual, they said tau sub A. I'm not kidding. That's. Yeah. I hope they don't change this 26 times. But by doing that, you're encouraging them to change this 26 times. All right. Let's take column AB first. All right. Let's take PU over FYAG. And from here on, first off, I think the slide says 50 KSI, but I think from here on out in this class period, when in doubt, FY is 50, because all of our design aids are going to be referenced from here on out based on 50 KSI. So AB has a load of, we said, 1070 kips divided by 50 KSI times 26.5. What? Did I say 1050 or 1070? 1050. Yeah, I said 1050. I'm sorry.
So we're back up to 76?
No. I'm going to write that clear. 1050. That's close enough. All right, so what do we get for this? 3 decimal places, we'll say.
0.792.
Okay. So this column is seeing a load up until about, we'll say, 79% of its yield stress. So that means we're probably going to have some inelastic effects, considering the fact, again, we've got geometric imperfections, we've got residual stresses. So we're not talking about an A505 specimen in the lab. We're talking about a 14 or 12-foot long column or what have you. Okay. So what I propose is, because of this, your tau value is 4 PU over FY AG times 1 minus times that. Sound good? Y'all seeing where I'm getting that? Okay, now watch this. 1 minus this fraction. What is this fraction? We already did that calc, right? 4 times that fraction. So instead of plugging and chugging all this stuff again, I'm just going to say 4 times 0.792 times 1 minus 0.792. What's that? It is, isn't it? It's pretty cool. So what do we get?
0.658.
0.658. Second on that? Yeah. This tau formula is a lot simpler than the previous one. The previous one had logarithms and stuff like that, so a lot easier. Now, this is for column AB. If you do column BC, you'll end up getting a tau value. If you go through and do all the math, you'll get a tau value of about 0.830. Yeah, 830. So again, same thing, okay? Same thing. So, here's your area, your load's 1370, go through and chug it, you'll get tau B is 0.3. So I'll say, or 0.83. So I'll say tau B is 0.83, and I'll say after calcs. All right, so now let's do, and then we'll call it, let's do inelastic Kx values. All right? So for column AB, we have tau GA, which is what? 0.792 times, what was GA? What was the original GA? Yeah, you're right. Oh. Now that one, I'll give you a half a mistake on that one. We're not there. No, remember we're back down to 2. Oh. I just had that one. All right, what do we got for this? Oh. So we'll say 0.63.
.624 times 9.
So,
No.
okay. All right, what was the G value for B?
2.19.
All right, so what do we got for this?
1.42.
Say it again, 1.44?
Yeah.
Well, I'm going to say 1.45. Nah, just kidding. 1.4. All right, so if we've got 0.62 and 0.44, now what's our new K value? What's our new K value?
$1.31.
1.31? Okay. Is that lower than what we had before? What did we have before? 1.45, so we're doing a little better, right? Okay. Real quick, we'll do BC and then we'll call it. Okay, so BC, we're going to have tau GB. Now, we're doing a different column, so it's a different tau value. In this case, it's 0.83 times 2.19. So what's that? Say it again. 1.82. Okay. Now, here's one thing. You're going to be tempted to do this, right? Tau GC, right? Don't. It's just 10. You don't apply any elasticity to a pin or to a roller or to a fixed support. There's nothing there. So what do we get here? Not to the ground, because there's no frame there. And remember, those fixed supports are mathematical constructs anyway, so the whole concept of yielding and all that doesn't really make a lot of sense. Say it again?
2.09.
2.09.
Oh.
See, I'm getting 2.07. I'll go with 2.09. See, I got the way I came up with my solution is I goal seeked it. So I'll say 2.09. But yeah,
This is what we're talking about for the exams.
that's fine. That's fine. Okay, before we call it, real quick, these are all kx values. What's ky for these columns? 1. Because brace frame in that direction's got to be somewhere between 0.5 and 1. We just assume the worst case. Sound good? That's all I've got for today. On Wednesday, we're going to talk about design, and then we're going to have a really sort of beefy design example. So, what's that?
That's a pun.
No.
We're not actually dealing with beef like designing a slaughterhouse.
Remind me of a Monty Python skit there. All right, that's all I got. I will see you all on Wednesday or in a couple minutes.